Okay. So thank you for coming to my talk on fuse collapsing for wide BVH construction. So real-time ray tracing is currently a very active area of research in computer graphics, as it allows for elegant implementations of various lighting effects, such as direct lighting from area lights, reflections, or even solving the full rendering equation using path tracing. However, to be practical, these ray tracing queries need an acceleration structure. So the goal of such an acceleration structure is to find intersections between a ray and a set of triangles efficiently. And the current de facto standard is the wide bounding volume hierarchy, or BVH. So a BVH is simply a tree on the primitives of the scene, where the leaves store the primitives and the internal nodes store a bounding volume of the corresponding subtree. And if all of the internal nodes have exactly 2 children, it's a binary BVH. And if the internal node can have up to n children, then it is a wide BVH. And so currently, every industry implementation that I know of uses a wide BVH with a BVH width that can vary depending on the architecture or the manufacturer. But this is basically the de facto standard. So, of course, a key challenge for real-time ray tracing is to build these acceleration structures efficiently on a GPU to be able to leverage the massive parallelism and memory bandwidth of our machines. So a pretty important use case in this context is complex dynamic scenes such as this one, where we have changing topology and significant deformations, which makes it impractical to reuse acceleration structures from one frame to the next, which means that we have to rebuild, and this is extremely expensive. And so the focus of our paper in this context is reducing this build time at the cost of some tracing speed, which is still worth it when build code is a bottleneck for complex dynamic scenes such as this one. So of course, this is not the first paper to tackle this problem. This is a very long-standing problem in real-time ray tracing research. And so I've shown here some of the papers that have come out, and some of them at HPG along the years that tackle this problem. And what I would like to point out here is that the vast majority of these papers until last year basically focused only on building binary hierarchies, while, as I've shown, the current de facto standard is the wide hierarchy for various reasons. And so last year at HPG, the paper H-block by Benton et al. Proposed both a very efficient binary builder and a separate collapsing step that transforms it into a wide BVH. So their pipeline looks something like this. They have a triangle list as input. They use a bottom-up binary builder based on the Pluck algorithm to compute a binary BVH, and then as a second separate step, they collapse it into a wide BVH. And we see in the results of their paper that this top-down collapsing step is actually one of the main bottlenecks of the pipeline, as it actually takes more time than the binary builder for complex scenes. So the goal of our paper is to eliminate this additional top-down traversal and to fuse a very simple collapsing procedure with a bottom-up builder to directly compute a wide BVH from our input triangle list. Since we don't have an additional traversal, we maximize the build speed, and this comes at the cost of some tracing performance, since our collapsing procedure is a bit simpler. So to explain our contribution, I am first going to detail our bottom-up collapsing procedure as a separate algorithm that takes as input a binary BVH, and then in a second step, I am going to explain how we fuse it with a bottom-up builder to compute this wide BVH without an additional traversal. So our bottom-up collapsing procedure works by traversing a binary BVH from the leaves upwards to output a wide BVH. And it is very simple, so we store up to n/2 references for each internal node. So, for example, for a 4 wide BVH, we could store up to 2 references per internal node. And so we propagate these references upwards from the leaf. So, for example, the node 9 here will store the references of its children 7 and 6. And then as we go higher in the tree, we check at every node if the references that are coming into this node have more than n/2 elements. For example, for the node 13, we have 4 references coming from the children, and so we create a new wide node with these references, and we set the set of references for this node as a reference to itself. And so we continue with this bottom-up traversal. We apply our criterion at every step until we reach the root, and this gives us a wide BVH. So the important point is that this collapsing procedure is very simple, and it works bottom-up, so we can fuse it with a bottom-up BVH builder. And the algorithm that we are going to fuse our collapsing procedure with is the Plock algorithm. So this algorithm was presented by Meister et al. In 2017. And it is basically a bottom-up binary hierarchical clustering algorithm. So we have here the array is an array of clusters, which is initialized with 1 cluster per primitive. And we compute, so this algorithm is separated in 3 stages. So we first have a nearest neighbor search, which is going to compute for each of these clusters its nearest neighbor. So we iterate over a search range. And for every neighboring cluster, we compute a combined bounding box, and we find the smallest one. This gives us a nearest neighbor for this specific cluster, and this is done in parallel for all clusters. And then the second merge step only operates on the pairs of clusters that are each other's nearest neighbor and merge them together into a new cluster. So for example, if we look at the clusters 0 and 1, we're going to merge them into a new cluster numbered 8. And since we merge 2 clusters into 1, we have empty slots, which are removed by the last stage, which is the compaction step. And so this is the core of the block loop. It is then iterated until there is a single cluster remaining, which gives us a binary BVH. And so our goal is to integrate our bottom-up collapsing directly within this loop. And to do so, we store up to n/2 references per cluster. So we store our references directly in the block clusters. And we do not modify the nearest neighbor step, so we still compute nearest neighbors between pairs of clusters as done by the Plock algorithm. And then during the merge stage, we apply the procedures that I described to merge together the set of references. So for example here, since all of the input reference sets have only 1 element, we get reference sets with 2 elements for the second stage. And then during the next iteration, we have sets of references with, for example, 4 elements coming in. And so we create our new wide nodes, basically in the same manner as I described for the bottom-up collapsing. And so this way we get a fused collapsing procedure. And one of the kind of interesting points about this procedure is that it actually only needs to modify the merge phase of the Plock algorithm, so the nearest neighbor and compaction step are not impacted, and so you don't have to read the code. That's not the point. The point is that this change is pretty self-contained. We only need to add a little bit of logic into the merge phase to basically merge together the reference sets and create the wide nodes. But otherwise, the structure and the rest of the code is untouched. So it is pretty easy to integrate. Okay, and so when we apply this procedure, we observe that it gives trees with pretty different characteristics compared to the top-down collapsing that basically goes from the root of the tree and merges the child node with the highest area into the current node, and then goes to the lower levels. So first, what you observe in the first row is that the top-down collapsing basically produces trees which are very full at the top, and then as we go deeper in the tree, the nodes have fewer and fewer children. While ours, interestingly, gives basically a constant number of children for every level. So, however, this is not really a good property, since we would prefer to have nodes that are full at the top of the tree, since having unused slots at the first level is a bit wasteful. And this also leads to deeper trees, as we can see on all of the graphs. And we have a lower rate of decrease of areas as the depth increases. So these are not very good properties for ray tracing, but we show here a pretty simple trick that alleviates some of these issues, and this trick we call the merge penalty. And so the idea is to slightly modify the nearest neighbor search so that we try to nudge the plug builder towards merging clusters that are going to give full nodes, to nodes that have no empty slots. And to do that, what we do is that during the nearest neighbor search, when we compute the distance between clusters, we check if they have the same number of references. And if that is not the case, we multiply the distance that we computed by a factor alpha that is greater than 1 to basically penalize this merge, which will tend to result in nodes that are not full. So for example, in this example, if we compute the nearest neighbor of the cluster in red, if we compute the distance with its left neighbor, since they have the same number of references, we don't change the distance. But if we compute the distance with the right neighbor, since they have a different number of references, we cannot penalize this merge because it would result in a node that is not full. And so we see that with this slight tweak to the plug builder, we can increase the average number of children per node for both the 4-wide and 8-wide BVH. And we get shallower trees and trees which have where the rate of decrease of node areas with the depth is higher. So it works pretty well for the 4-wide BVH, as you can see. For the 8-wide BVH, there is still an improvement, but it's more minor. Okay, and so now I'm going to show you some results. So we compared our fuse collapsing algorithm using hblock as a binary builder. So I use block in my explanation because it's basically the same algorithm, but hblock is a variant that does all of the iterations in a single dispatch. It's a bit more complex, but the idea is the same, and the integration of our fuse collapsing is basically identical. And so we compare hblock with fuse collapsing, which is our method, with hblock with top-down collapsing, which was described in the hblock paper. All measurements are done on an NVIDIA RTX 3090. We evaluate both 4-wide and 8-wide BVH on 4 complex dynamic scenes, which is the target of our method. And we benchmark using 1 diffuse secondary ray per pixel at Full HD. And an important point is that this is done using software ray tracing, because the hardware ray tracing APIs are not flexible enough to allow us to use our own bounding volume hierarchies, so we have to use software ray tracing, which is a bit of a shame, but still the results are still significant. So I'm going to show you some results, but there is more in the paper. So first, the scenes that we use. Okay, so the main point of our method is to reduce the build time. And we do observe a consistent reduction in build time across all scenes. So this is the total build time, so counting the sorting steps and other miscellaneous steps. And we do observe a pretty consistent reduction in build time for all of the scenes, which is the main objective of our algorithm. In turn, when we measure combined time, which is the sum of build time and trace time, this results in a lower combined time for these scenes where the total time is basically dominated by the build step, which is very expensive. So this is the main target of our algorithm, and we do manage to gain a pretty consistent improvement in this configuration. However, as I've explained, our trees are a bit lower quality than produced by top-down collapsing. So if we measure the SAH, for example, we tend to have higher SAH because our collapsing doesn't really optimize directly for lower node areas. So we tend to have higher trace times. This is very scene dependent, so it can be as low as 11% in our scenes, or as high as 37% on one specific scene, which is quite significant. So in conclusion, I personally believe that building wide hierarchies is currently an understudied problem. As I've discussed in the introduction, most of the literature focuses on building binary hierarchies, which is something that I think now we are getting pretty good at. But since the current standard for actual ray tracing implementations is the wide hierarchy, I think there is really room for research on this specific problem. So in this paper, we propose a construction algorithm that focuses on a specific trade-off where we want to maximize build speed. So this is a, let's say, one data point in what's possible in the space of building these wide hierarchies. But I really believe that there is room here for new approaches that look at different trade-offs, or even revisit ideas that maybe didn't completely work out for binary hierarchies, but might make sense in the context of wide hierarchies. And yeah, I think this is really, you can try it for yourself, try to solve this problem. I think you might get some papers out of it. So if you have any questions, I would gladly take them.
Thank you. I'm going to do a question since it's my prerogative. In the paper, you said your nodes are 48 bytes in size, but typically a cache will have 64 byte or 128 byte lines. Yep. Is there any need to? Would you be better off trying to pack more into your node and make it a bit bigger? And
sure. Okay. So so what we did is that we started with the 8 wide. Node, we use the format from the compressed wide BVH by Eliti et al. So we use that as our starting point, and then we just, to basically stay consistent with software ray tracing state of the art. And we kind of just adapted it to the 4 wide format, which uses 48 bytes. And you're right that it would make sense to, I think, to as you said, maybe pack more into it. It's a bit tricky because if you, you can either use these additional bytes to give more precision to your bounding boxes, or to maybe pack more bounding boxes. Using more precision, I don't think would give a lot of mileage, because the 8-bit quantization works pretty well, and using having wider BVHs, I think would make a lot of sense in a hardware ray tracing context. In software, maybe we would get, I think, compute bound, and yeah, and so we could try it. We haven't done it. We could try it. Maybe it would work better, but I'm not sure.
Great presentation. One quick question. So even if you penalize, let's say, the distance in the merging phase,
yep.
right, you don't get really full nodes, right, where all children are kind of set, right?
Yep.
Any ideas how to get this, right, from, let's say, I'm not sure about your utilization, 80, 90%? Inner node utilization, something like that?
Yeah, we have it in the paper. We actually have higher utilization on average compared to top-down, because since we have like, if you look at the curve, most of the nodes are not at the top of the tree. So if you look at the average slot utilization, it's higher for our method, but I mean, this metric is a bit doesn't really represent the.
But what you want to have is full utilization at the top of the tree.
Yep.
Right? And I don't think, does your method guarantee this? I don't think so, right?
It doesn't.
Any ideas how to get this? Another path?
I mean, we could. I didn't get your last sentence.
Basically applying another path, maybe.
Oh, yeah.
Still.
So we haven't tried it. Yes, we could do top-down for only the first levels. Maybe it would work. We have something similar for another problem. So this is not related to really the slot occupancy, but we do a pass on the top of the tree to reorder, because as Simon said, since our nodes are not cache line sized, we have to consider the ordering of the nodes, And so for implementation reasons, our ordering is not deterministic. And so we do a top-down pass on the top of the tree to compute the breadth first order. So we could consider using, during this same pass, maybe trying to fill the nodes that are underused. It could, yeah.
Thank you.
Hi, fantastic presentation. So I have a question that's maybe similar to the question that was just asked. Is have you thought about like increasing the penalty as you get higher in the tree, or I guess closer to the root of the tree, in order to, I guess, incentivize this like top-weighted structure?
So no, we haven't tried. That's an interesting idea. I'm not sure how we could go about this, because since this is bottom-up, we don't really know where we don't know the level of the node when we're building it, because yeah, so it's not that simple.
Right. Okay, thank you.
Probably have time for one more question. No? I was going to ask, the 1.3 weight, was that identical, both the 4 wide and the 7 wide? Because you seem to concentrate on that.
We use the same for both. We experimented and we found that, we basically tried multiple values and we found that 1.3 worked well for both. I don't remember if there was like a specific best parameter for BVH for BVH 8. I don't think so. I don't remember very well.
No more? Well, as we have a little bit of time. One more question then. So you start with single triangles. Did you experiment with pairs of triangles? Because they're quite popular.
Yeah, no, we haven't. So this is something that I think would be interesting to try. We haven't, because at the start we tried to stick with the compressed weight BVH representation and implementation. So no, we haven't. I do think it would be interesting because it looks like this is a pretty widespread representation and it seems to be working pretty well. So I agree that this would be interesting to try out.
Okay, if there are no more questions, let's thank our speaker.
Okay.